Now we know how to use this transistor as a switch. And actually we have to consider only two different modes. One is cutoff mode, the other one is saturate mode. Today we can discuss the other applications. We can use transistor as an amplifier. Let me share a new document with you. And you can take blank document. You know that how to use this transistor. But anyway, before we use transistor, you know that we have to turn on the transistor. To turn on the transistor, we have to fulfill two conditions there. One is we have to forward bias base emitter junction and reverse bias base collector junction. Okay. This is the transistor. To arrange all these things, to provide that proper voltages and currents to the conditions to the transistor, we have to arrange certain things. Okay. Then arranging of all these things means that we have to put certain components there to do those conditions. First one is that we have to forward bias base to emitter junction and reverse bias base to collector junction. Those are the two things we have to do. Okay. There, to do this one, and we are taking voltages from this supply. And here we have supply voltages from 0 volt to plus VCC. We have certain voltage. From that voltage, we have to take some voltages and currents to do these things. Okay. When you apply certain things there, okay, when you arrange certain there, for example, to do this, you have to provide it. To forward bias base emitter junction, we have to provide certain voltage to the base emitter junction. Okay. Then to reverse bias the base to collector junction, again we have to provide certain voltage to this junction. Providing voltage means that there is no other way, that we have to take those voltages from this source voltage. Okay. Then the way of doing that one, arranging the component, that one means that we say this is transistor biasing. Transistor biasing. Before you use a transistor, anyway, that when we use this transistor as a switch also, we have done this biasing. Here also the transistor biasing is important, but when it comes to the biasing, there are many modes. There are many methods are there to bias the transistor. But here we are not going to discuss many methods here at the moment, and we are focusing a very simple method here, how to bias the transistor. Okay. To do that, we consider a very simple method here. And this way, we have this trans resistor. We have this resistor. And depending on the values of this resistor, the voltages at this point, this VB and this VC will be varied. Okay, here that this VE, this one, it's almost zero here. But other two things, this collector voltage and base voltage will be different based on the resistor values we have used here. Okay. The simple arrangement we can do to do this one. And can you consider this diagram? I'll draw a common diagram for this one. Then here we can apply resistor here. This is collector resistor. This is emitter resistor. And likewise, we can put this one is base resistor. And the voltage we are providing for this one, we can say this is plus BB. That means base voltage. Okay. Likewise, we can consider this common diagram. In this common diagram, you can see we have 0 volts, and with respect to the 0 volts terminal, here we have plus VCC, collector voltage, collector voltage, and here we have another resistor. Then it's coming from BBB. Sometimes that this BBB VCC may be the same, but for the moment we keep it separate. It's a common thing. But then after that, the currents. This is IB. This is IC. And this is IE. Okay. For this one, considering this one, we can write a general equation for this. That is, starting from this VCCN, then VCC equal to this voltage drop ICRC plus this voltage VCE plus IERE. Is it okay? This is a general equation. We can write from plus VC to 0 volts. Then using the Kirchhoff law, we can write plus CC equals to ICCRC plus VCE IER. But you know, that IB is very small with compared to IC. And this relationship is also there. IE equals to IC plus IB. Therefore, we can rearrange our previous equation like this. VCC equal to IC, RC, VCE, and this one, from this we can say this is IC, RE. Okay. Is it okay? Check that whether it's okay or not. And here that IB is very small one, and because of that, we can write this one IE is very much close to IC. That's why we wrote the second equation. Okay, now we can rearrange this equation. We can take IC to one side, then this IC RC plus RE, then the other side we have VCE plus VCC. Then IC equals to 1 over RC plus RE VCE plus VCC divided by RC plus RE. Okay, then this is a kind of equation. Something like okay. Then this M is minus 1 over RC plus RE. This is the gradient. And here you have intercept. C is VCC divided by RC plus RE. Because RC is a constant, RE is a constant, VCC is constant, then C is a constant. This is the slope of this one. And do you remember that the graph we draw between this IC and VCE? Shall we draw it again? Then this is VCE and this is IC. And we had a do you remember this one? I think when we draw a certain graphs and we had this one initial. Okay. These ones are for different IBs. This is IB1 and IB2 like that. These are for different, sorry for the interruptions. IB3, IB4, IB5, like that, okay? IB6, and don't worry about these values for this relationship between this IB6 and IB5 like that. They are this way. Okay, now we can draw our line here, so that this is the graph between IC and VCE, and we should be able to plot our this equation on this graph. Then it will be something like this, because we have the minus slope. It may be something like this. Okay. Then when IC is 0, when IC is 0, VC is equal to, then here you can see that from the equation 1, shall we put here 1. From 1 we receive VCE equals to VCC. Therefore, here this point is VCC. Okay. Then when VCE is 0, from equation 1, what do we get? Now this is C. Okay. Then IC equals to here this point. This is VCC divided by RC plus RD. Sorry. Is it okay? Then we say this is because here we have considered all the DC voltage. So this voltage is DC, VCC is DC, VBB is DC, and here we don't have any AC voltage involved. Then we say this is DC load line. What is this? This is DC load line. This is the load line of this transistor circuit. Okay. And normally, the operational point, we have to identify the operational point of this transistor. That we say operational point is normally we select operational point in the middle of the Q point, in the middle of the graph. Then transistor has freedom to go either side, the negative side or positive side. It can vary, and then it can go anywhere. Then we can, the Q point is, the Q point means this is operational point. operational point, or we say sometimes quiescent point. This is quiescent point. Okay. Then how can we select operational point here? In the middle of this one. Then we put operational point somewhere here. This is Q. This is Q point. Okay. Anything difficult? Any problem here? Okay, now you know that for an amplifier, we can amplify both AC voltages and DC voltage. If you are going to amplify DC voltages, now we have this diagram, we have this circuit. You can use this circuit to amplify DC voltage. Then where can we give voltages here? To this point. You can give, I'll draw that circuit again. Then this is the circuit. This is 0 volts line, and this is emitter resistor. This is plus VCC, and we take, this is RC, and this is RB, and we can take, this is V out, and you can take this one as V in. This is our normal circuit we used. Okay. And what is the difference between this circuit and the previous one? Here, providing some kind of voltage here, we have taken this one Okay. The difference between this circuit and this one, here we have V input voltage. But you know that providing this VBB voltage here, we have pushed the transistor in this operational mode. Then this is our DC load line. To have this DC load line, we have to provide VBB, base voltage. Then providing this base voltage means we have biased the transistor. We have placed certain voltages. We have given certain voltages to the transistor, and we have arranged certain components to receive that voltages to the base terminal and the collector terminal. Then having arranged all these things, now we have this DC load line, and we put our transistor operational point in the middle also. To do that, we have to select particular IB, we have to select particular VBB like that. Otherwise, that we can't place the transistor operational point here. After placing this transistor means that here, if you don't have this voltage, base voltage here, transistor cannot work there. Then transistor will be moved this side. This is cutoff mode. This is saturate mode, and this is the linear region. And when we want to use this transistor as an amplifier, we have to make sure that we are operating transistor in this region, in the linear region, active region. Okay. And to do that, we have to push the we have to turn on the transistor and providing some kind of currents, IB or VB voltage like that. And we have to bring the transistor somewhere here. Then to do that, this arrangement is not working. Then we have to provide certain voltage to this point. Then these voltages are fixed. Now transistor will, we place this transistor operational point in the middle when we carefully select this RB and RC couple. After that, you can give another voltage here. Now this is your input voltage. Now this input voltage sorry, can be amplified by the transistor, and we can take that output from this terminal, collector terminal. Okay. Then, and with compared to the previous diagram, here we have VCC, and we put here VBB as VBB. Then VBB is this. We are receiving VBB through this RB, and our all other components are same. And same diagram, this one is the previous one. There is no difference between this diagram and this one. Additionally, what we have put here is that we put this V in here, and we took V out from this point. This is input voltage. After arranging this one, we can give another DC voltage, then it will be amplified, and we can take it from collector terminal. So we have. Okay. Okay, that is for DC voltages. But what about AC voltages? For AC voltages also, and we have to have the same arrangement. Then to give AC voltage here, here we can but for AC voltage, how can we give AC voltage? And we have to do small modification here. Otherwise, we cannot give AC voltages. we have to provide AC voltages to a capacitor. This may be some AC voltages coming from this way, something like this. Then otherwise, sir, if you directly couple this AC voltage input here, then this DC component, the DC voltages are coming from this VCC side, and this V inside, they will get clashed. Then to avoid that one, to avoid that the danger coming from this side to this voltage input source, the signal source, we have to put a capacitor in between this source and the circuit. When you put this one, only the AC voltage component will be transferred through the capacitor, and this DC component coming from the amplifier side to the voltage signal source will be blocked. That's why we put this capacitor here. Okay, we say this is input capacitor, C in. Okay. Now, this is a bit not difficult one. It will be sometimes it may be to understand this one that you have to think about this one about the AC component only. Now this is the one. Here this VCC is a DC component. This VCC is a DC voltage. This is DC voltage. This DC voltage can go through RC, through RB, and all the places throughout the circuit. DC voltages can go. But here we are providing AC voltage. This AC voltages is going through this capacitor, and it can go here. Then for the AC voltages, consider that one. For this AC voltages, we can redraw this diagram considering only the AC voltages. This is RB, RC, RE, and through this capacitor, okay, through this capacitor, we are receiving AC voltages here. Then we have this IB, the AC current coming from this one. And here, this current from the source, another current can go through IC that we say this is simple IC. Simple means we show this AC component. Okay, then this will be IE. And this is V. G. Okay, then we can write our new equation for considering AC components only. Then we have this, but we don't have, when you consider this path, we have considered the previously this path, you may remember it. Consider this VCC to 0 volts, this path, this we wrote this equation VCC equals ICRC plus VC IER. But here, when we consider this one, we can write equation like this, because here we don't have DC voltages at this point. Then 0 volts, zero equals to IC RC plus VCE plus IE RE. But you know that IC is very much larger than IB. Then we wrote this, we can write this equation ICRC plus VCE plus ICRE. Then like previous one, we can rearrange this one. And after that we can receive IC equals minus VCE divided by RC RE. The same slope we have received, same slope like previous equation. For the DC load line, we received, the slope was minus 1 RC plus RE. For AC component also we have received 1 minus RC plus RE. Okay. The meaning is that we have, when we draw this equation, for the AC load line also we have Slane flow. Okay. For the AC load line also we can draw it here. In the practical circuit, both AC and DC load lines should go through the Q point. And say therefore both load lines are coincident. Because of that, both lines are having the same slope. Okay. In our AC load line also, having same slope. And passing through the same Q point. Then whatever the signal we are giving to this AC signal or DC signal will be amplified by using the same slope. Okay. How can we set this Q point? By selecting suitable values for this RC and RB. By selecting suitable values for this RC and RB, we can place this Q point anywhere in the graph. Okay. Then we have to carefully select. We can select Q point. Setting or selecting suitable values for the components. Used in the biasing. To bias the transistor, as I mentioned earlier, to bias the transistor, we have to select these components, RC, RB, like those things, and RE also. Okay. Then we have to select this component, and after selecting this component, we can calculate the voltages and currents going through that one. Then we know the beta value of the transistor, and based on that, we can find all the values there. Then we can recalculate this RC and RB to put suitable currents and voltages in this circuit. The meaning is, then we can place this Q point, whatever the place we need, by selecting the suitable values for these components. After doing that one, this is our graph here. Sorry. Then what can we do here is that then we can do whatever the changes with this IB here. We can do the center value of this Q. We can apply some AC voltage here, something that like this. Then when we apply this AC voltage here, with this time, this may be T, and this is IB0, and this may be IB1, and this is IB2. Then signal is varying like this. Then this is the input side that giving some kind of the varying current to the base terminal will be reflected collector terminal. Why? here with that, what type of changes we can see here? That is the changes of IC. And when, if you consider this is the time axis, the time is changing like that, then when you increase IB current, then you can see the increasing IC current also. And when you come down, and from IC side, this is the waveform you are receiving. Then this will be, this is IC 2 and this is IC 1. This one. We can see this change. When you input this type of volt current, you can identify that one. Then you are the AC waveform you are providing this one. When you provide this one, the IB will be changed. And when you input some kind of AC voltage like this, when you input some AC voltage like this, then here at the starting point you can see, and you are increasing certain voltage here, then it will be applied here. When you apply this voltage here, this voltage will be coming to the other side of the capacitor. Then through the capacitor, AC voltages can be gone, but DC voltages cannot go there, cannot through it, it will be blocked. But AC voltages can go through the capacitor. Then AC voltages can go through the capacitor means this increasing voltage will be appeared at this point. Then it will be collected with this voltage coming from the VCC side, and then at the base point, then this RB through RB, the increase in voltage will be coming here. This voltage, although that here we have some kind of voltage here, in addition to that, certain voltages are increasing here. And as a result, IB will be increased. Because transistor doesn't know the voltage is increasing, but transistor sees IB is increasing. When IB is increasing, as a result, IC will be increased. Okay, this is IB. IB will be increased. As a result, then IC will also increase. When you increase IC, what about ICRC? ICRC will be increased, but VCE is reducing. When you consider this half cycle, here when we apply this half cycle here, something like this, then for this is for IB. Then IC also following same one, but little bit increased one. But when you have this high wave from the increasing IC current, but when you consider this one, what is this one means? This VRC and VCE. VRC, what about VRC? VRC is also increased. Then VRC also increasing. This is VRC. But when we increase VRC, here VCC is fixed. But here you can see the increase in voltage will be appearing here. Because of that, to compromise that one, to balance out that one, how can we balance out? Then VCE should be reduced. You can see this equation. This equation you can see here, VCC is fixed. Then ICRC is increasing. But this is fixed. Then what should be reduced? this should be reduced. When this ICRC is increasing, this should be reduced. Otherwise, that how can we balance this? Because BCC is fixed value. Okay. And as a result, here you can see the changes of VCE. When you increase IB, IC will be increased, but at that time, sorry, at that time, proportionally, VCE is decreasing. What did you see here? I draw this diagram again. This is 0 volts. And this is V out. Actually, what do we take as V out? It's this one. Then when we input a voltage like this, here in the positive half cycle, IB is increasing. As a result, IC is increasing. When you increase IC, ICRC will be increased. Then to balance out that one, VCE should be reduced. Then here, this side, we can see reducing VCE. And when you reduce V in voltage, as a result, IB will be reduced. When IB is reducing, IC also reducing. Then ICRC reducing. Then VCE will be. Then you can see this is the input voltage, and this is the output voltage we are receiving. Is a 180 degrees phase shift is there. And this is simple A, simple B, and as a result, this is the amplified version of AB. Is it okay? Any question? Here also, to take the AC component voltage only from this side, we have to put a capacitor. Okay. Then this is C1. See. Then C1 and C2 capacitors. Allow AC voltages go through them, but block the DC voltages. Going through them. Then for this side, DC voltages cannot go to the V inside. And here the DC voltages we have supplied from this VCC line. And it cannot go, the DC component cannot go to the V outside also. Then when you input AC signal here, from V out, you can receive AC signal only. The DC component will be blocked. Actually, the biasing method we have, I'll remove this one. And we have many biasing methods. Actually, this biasing method is, this is and we have directly given to this one. And because of that, we say this is fixed bias method. This is fixed bias. I'm showing you that only the different type of biasing methods. But when you do the calculations, that you can understand that how these things are different. In this fixed bias method, the same biasing method is there, but we have some kind of differences here. In addition to that, it's RE capacitor. See, RE1. Here we are putting another capacitor. Like this. Then why do we put this one? This is C3, something like C3. Okay, when we put this capacitor, through that capacitor, through the resistor, DC component can go. But through the resistor, through the capacitor, DC component cannot go. Then it is not necessary to do this DC component to have another path, because the already DC component, the DC voltage can go through RE, then it can go to the ground side. The DC component coming from VCC, this end, the top end DC component is DC voltages are coming here, and it can go through RE. Because of that, it is not necessary to DC component to go through C3. But why do we put C3 here? You can see here that when we write equation for this AC component, do you remember the previous one? We wrote this one. When we give this AC voltage V in here, and we had this simple IB, that is AC component, and this simple IC, and this one IE. We put this IE because that RE resistor is there. Then because of this resistor, that effect is also having to this AC value. For example, we wrote this equation 0 equals IC RC plus VCE, and then IER. Okay, IER. But here, when we rearrange our equation, you remember we had the same type of equation, then IC equals minus 1 over RC plus RE VCE. Then slope was minus 1 over RC plus RE. We show that the same slope we have for this DC line also. But when we have this capacitor here, because of this capacitor, this AC component can go through C3 without having any effect. Okay, without having any effect, the AC component can go. Then this DC component has no block. Then through capacitor, it can go to the ground side. Then this effect of RE is not there. Because of that, we say we rewrite our equation with this one 0 equals IC RC plus VCE. Then this one is not coming. Then we can write our equation IC equals minus 1 over RC VCE. Then what is slope? Minus 1 over RC, not RE plus RC plus R. Then what will happen? You remember this one? In this case, we have coincided AC load line and DC load line. But in this case, when you rearrange this circuit like that, when we add this capacitor there, we have same Q point, but we have a different AC load line. This is DC load line. Slope is 1 over RC plus RE. And this is AC load line. Slope is minus 1 over RC. But we are putting same Q point, then we can change the slope of this AC load line. Then for the DC operations, we can consider the DC load line. For the AC operations, we can consider AC load line. Okay. Then that change can be common for any type of biasing methods, but this is the fixed bias method that we have used so far. And the second biasing method, next we are going to discuss. Actually, I am not going to discuss, many biasing methods are there, but we are not going to discuss all these biasing methods. I am going to discuss only another one. This is the second method. Actually, we have many methods, but we are not going to discuss all. And the very common biasing method I'm going to discuss is, this is self-bias. Self-bias, we have different names for this one. This is, we say this is emitter bias, or maybe stabilized bias. Actually, among all the biasing methods, this is the most stabilized biasing methods. Okay. It has certain change here. not like this. This way. And this is R1, R2. This is a voltage divider. With this voltage divider, we can place any voltage at the middle point. Then we can calculate this middle point voltage based on this RE and the required VBE value. Actually, what is the very important thing here? Why do we say self bias? Then you know that when the temperature increases, if you recall our previous lecture, the first lecture, do we remember that we said that in the semiconductor materials, when temperature increases, the free electrons will be more. Okay. When we have more free electrons, the conductivity is increasing. Then, although that we have calculated these resistor values here to put this Q point here, now when the temperature increases, the Q point will be shifted. Why? The resistor values may be there, but the transistor conductivity, inside transistor conductivity is increasing with the resistor, with the temperature increases. Then Q point will be shifted. Then we have carefully selected this RC, RE, RB values to put our transistor in the middle point of the graph. And we, after that, put in that one, our Q point may be in the middle, operational point may be in the middle. But when the surrounding temperature increases, the circuit temperature will be increased. Then the transistor inside temperature will be increased. Because of that, the free electrons will be increased. Then the inside conductivity of the transistor will be increased. Then it will be badly affect to the circuit operations. But here, because of this temperature increases, we say this temperature is increasing. As a result, what will be the HFE or maybe beta is increasing. Then as a result, IC will be increased. Then IC is increasing means, then what about that when we increase IC here in this circuit, IC is increasing. This is IC. And IC is going through RE. Then because of that, the voltage across this one, the RE resistor will be increased. VE will be increased. When we increase VE, this voltage, when we increase this voltage, what about the VB? See this one here, we have certain VB voltage. It is fixed because of this this resistor divider circuit. At this point, VB is fixed, and here we have VE. Okay, this VB is fixed; it is not changing because of anything. Why? We put this R1 and R2. Anything can be changed here. Any signal can go there, but it doesn't matter because of this resistor divider network. This point voltage is fixed. Then VB is fixed. But when the temperature increases, HFE is increasing, SFE is increasing, means IC is increasing. When we have increased IC, as a result, VE is increased. When VE is increased, what about VB? Definitely VB is decreased. VB is decreased means then IB will be decreased. When IB is decreased, as a result, IC will be decreased. Then you can see here, due to the temperature variation, temperature rises, then IC will be increased. but it will be stabilized by this one. When IC is increased, BE will be increased. When BE is increasing, this BB, this point voltage is decreasing. As a result, IB is decreasing. When IB is decreasing, definitely IC will be decreased. Okay, those are the things actually I'm going to discuss about transistor amplifiers. We have many other things to discuss, but we are not going to discuss all these things here. Any question? Okay, shall we have small exercise? Then you can understand this one and you will see that which type of questions are coming. This is 0 volts line. Okay, we can take R1 10K, R2 5K, and this RC is 1K, RE 2K, this is so this is C in, this is capacitor, collector capacitor, only this output capacitor. We can say this is emitter capacitor. This is C out. Okay, then draw DC load line. Okay. Then B determine Q point. Okay, you can take this VCC. This is plus 15 volts. And to determine the Q point, you can take VBES 0.7 volts. Then for DC load line, do you remember the equation? IC equals minus 1 over RC plus RE, VCE plus VCC divided by RC plus RE. Okay. Then this is VCE axis, this is IC, and this will be the load line, but we don't know values. But then when IC is 0, when IC is 0, we receive this point. Okay, the maximum it can go up to VCC. Then this is VCC. VCC means here this is plus 15 volts. The other side, VCE is 0. When VC is 0, and we have this one, we have IC equals VCC divided by RC plus RE. Okay. and this is maximum. I see. VCC is plus 15 volts. RC is 1K. RE is 2K. Correct. RC 1K, RE 2K. And this will be 15. This is 5 milliamp. Okay. This is 5 milliamp. This is DC load line. Then we have to determine this operational point Q. Okay, based on the values available, simple B to find operational point. Then where can we start? Then here, when you consider the circuit, this is AC, and this is IE, this is IB. Okay. If you consider this point voltage, this VB, this is 10K and this is 5K. Because of that, at this point, the ratio is this should be 5 volts. Considering voltage divider, VB is 5 volts. Okay. Then we can calculate IE current, because the voltage at this point VE, this is 0.7 volts drop here. We have 0.7 volts drop here. Then we can find VE. And because of that, VB is 0.5 volts, then VE is equal VB minus VBE. Then 5 minus 0.7 volts, it's 4.3 volts. Then we can find IE current. .3 volts divided by 2K. Then this is 2.15 milliamp. But we are considering this IC is close to IE. Because IB is negligible one. And here we can find this VCE voltage because we don't know VCE voltage here. But VCE volt we can write equation VCC equals IC RC plus VCE, then IC RE. Okay. Then VCE equals VCC minus IC RC plus RE. So 15. Minus, you can cancel out this one. 2.15, it's a 3. Should be 2. 3 times 0.45 minus 6.3. Then VC is 8.55. And we have to find VCE. Then we have to find collector current. If you know that one, then we can mark this one here. This is 2.15 milliampere, and this is 8.55 volts. We have placed Q point at these values. Yes, at this time, that we have to ignore C capacitor because that we don't want that. But anyway, that DC voltage is going through RV. Then based on that, we have to do this calculation. This is the IC value. This is the VCE value. Then these are the two things, and we have to find to plot Q point. Actually, Q point is determined by selecting these components. I think you have realized this one. When we select these components here, then we have selected the Q point location. In other words, if you want to change the Q point location, you have to change these components, component values. Okay, that's what we have to discuss under transistor amplifiers. Any question? Anything? Okay, this may be a little bit, it's not difficult, but because of these things may be new, because of that you might feel some kind of strangeness here. When we do the exercises, and it will be okay, and I'll prepare tutorial and putting some questions there, then we can discuss them tomorrow. Okay. We'll meet again tomorrow morning, I think at 8. In the morning, we can discuss digital electronics tutorial, and the evening we can discuss analog electronics tutorial. Both tutorials I'll send to you tonight after preparing this one. Then when you have any kind of questions, that we can discuss those questions tomorrow. And if you have any questions, then feel free to ask me. And I think at the moment, some of you has already sent me some questions for the digital electronics side, that you have drawn certain waveforms and anything, the timing diagrams. And I'll check that those things. Still, I wouldn't do that. I'll check that one and I'll ask those questions. And I'll upload all these documents, the videos and this document to you. And then I'll send all these links today. Okay, you can bring tomorrow any questions that maybe the past papers questions or whatever the thing, and we can discuss those things tomorrow in addition to the tutorial. Okay, then shall we end the class? Okay, I expect your participation tomorrow also, and you can bring many questions there. We can discuss those things there. Okay, then shall we wind up the class, and shall we stop now? Okay, thank you very much for your participation, and we'll meet you tomorrow.
Thank you, sir.